Within the past year, chemical and mechanical engineers collaborated on the Open Insulin senior design team to develop an at-home generation device that could be used to synthesize medical-grade insulin. This project was derived as a continuation of an industry-scaled insulin production model from last year, with the intention of condensing the model into a small and simple device that could be used at home. The primary motivation was to circumvent patents and propose a synthesis method that reduced the cost of insulin to address the social injustice of exorbitant insulin prices in America. During the first semester, the team focused on literature and patent review, considering various insulin precursors such as yeast, proinsulin, and crystals. Insulin crystals were ultimately selected due to their enhanced stability and incorporated into the prototype design. The first iteration involved solid and fluid transport systems such as screw augers and pumps that introduced the need for a clean-in-place system. These constraints were then removed during the second semester, when the team focused on optimization of the device and created a second iteration that utilizes a vacutainer, thereby removing the need for CIP and improving the safety of the device. In the final months of the project, the team conducted laboratory testing to demonstrate the dissolution of crystals and explore potential quality control measures.
Insulin is a life-sustaining medication that is essential for millions of people with diabetes to manage their condition and prevent serious health complications. In the United States, there are 34 million people with diabetes and 88 million with prediabetes. For those with type 1 diabetes, insulin is a vital medication for regulating blood sugar levels. Despite the importance of insulin, the cost of the medication has tripled over the past decade, making it unaffordable for many diabetics. As a result, some individuals with diabetes are forced to ration or skip doses, which can lead to serious effects such as kidney failure and even death. In addition to it restricts a lot of diabetics from traveling, as there is no reliable refrigeration on road trips or airplanes. Therefore, our team has designed and developed an at-home insulin generation device in order to promote affordable and accessible insulin. This insulin synthesis device does not require refrigeration of solution before use, allowing for more convenience and flexibility to the user. With the prevalence of diabetes continuing to grow, the market is expanding. In 2019, the global insulin market was approximately $35.78 billion and is expected to reach around $62.9 billion by 2026. In addition to the increasing prevalence of diabetes, the growth is caused by development of delivery methods and growing demand for biosimilars. Target customers include rural areas, lower income, higher education, first responders, third world countries, and constant travelers. In addition to these business-to-consumer options, it may also be sold to hospitals and pharmaceutical businesses, widening the market segment. The current insulin market is dominated by three major pharmaceutical companies: Novo Nordisk, Sanofi, and Eli Lilly. These companies also sell a variety of different insulin products, from vials to pens and cartridges. Though these companies are well established and hold significant market shares, there is potential for a new entrant to differentiate themselves and capture a share of the market. Our design holds focus on differentiation and innovation that can contribute to the growth of the industry. Toward the end of our project, Eli Lilly dramatically changed their prices to $35 a vial, dramatically reducing the demand for lower-cost insulin. However, our product is still competitive due to the increased stability of lyophilized insulin crystals, removing the need for refrigeration. It provides much more convenience to the common user and will market to those that are without sources of consistent electricity and refrigeration.
As this project began as an extension of a previous year's senior design project, our first semester focused on understanding the fundamentals of insulin synthesis and what design considerations and constraints would go into a machine to produce insulin at home. It was quickly discovered that the scope of a machine to produce insulin from scratch would be far too complex to be viable for a product used at home. The block flow diagram on the screen details the complex insulin synthesis process. The first design simplification was made in order to combat this complexity. Our team decided to start the at-home synthesis process with an insulin precursor, which reduced the number of process steps required to produce insulin. Pre-insulin, pre-proinsulin, and insulin crystals were considered, and it was found that the processes for both pre-insulin and pre-proinsulin were still both highly complex and did not eliminate the need for complex lab techniques. Insulin crystals, on the other hand, were much simpler and only required the mixing of crystals with a buffer solution. This simplicity led us to move forward with the insulin crystals as the precursor for the remainder of the project.
Although the introduction of insulin crystals simplified the chemical process significantly, there is still a great deal of complexity with the mechanical design of the device. In this design for the device, all materials that would be used would be shipped in bulk to the customer. This includes an insulin precursor that would be manufactured in a factory, then shipped in a dry crystallized form, along with components for the buffer solution and the chemicals for cleaning. The device would then need to accurately dose these ingredients using screw augers and peristaltic pumps. moving the material into mixing chambers that would then synthesize the buffer solution. Finally, the buffer solution is mixed with the insulin crystals to produce the final product, injectable insulin. This solution still had its issues. Control loops were required to ensure the safety and consistency of the product produced, and in addition, once the insulin was finished being produced, a clean-in-place solution using hazardous chemicals was required to maintain the sterility of the system. All of this together made the system too complex for at-home use. The final design optimization was implemented to combat the complexity of the previous iteration in order to make the device more safe and sustainable. Instead of using a system of pumps and augers to transport the feed streams, the design was changed to include a vacutainer and buffer bag system. This also eliminated the need for a clean-in-place system, which made the process much safer for the user, did not require hazardous chemicals, and reduced the complexity of the system as a whole. To assist in validating and choosing designs for the prototype of the mechanical device, we created a list of constraints and requirements. The constraints and requirements used for every design decision were cost-effectiveness, sterility, reliability, and simplicity. These were derived from customer requirements, safety requirements, and FDA requirements. In addition, each design had its own specific functional requirements. For example, when picking the method of insulin crystal delivery for the final iteration, the functional requirements of material waste, device contamination, and ease of use were applied. These design considerations were then weighted based on their importance and applied to a decision matrix containing all of the design options being considered. Here you can see that the vacutainer was chosen as the desired method of insulin crystal delivery, as it best fit our design requirements.
Through the course of this project, our team made sure to consider the FDA approval process in our design decisions. In order to bring this product to market, FDA approval would be a necessity, and through research we found that one of the most important features required for a Class 2 medical device was quality control steps. Because this device is producing insulin that will be directly injected into a patient, the quality of the final insulin product must be assured. Our team began working towards developing quality tests to ensure that the insulin is safe for injection. All of the design decisions previously explained led to the final design iteration, where a vacutainer preloaded with insulin crystals is connected to a buffer bag containing the buffer solution. The vacuum present in the vacutainer pulls the buffer solution in, and the vacutainer is then moved into the mixer to ensure that the insulin crystals are fully dissolved. The final steps of the process are the pH and concentration tests, which will ensure that the insulin is ready for injection. The intricacies of each of these steps will be explained in the following slides, starting with the synthesis of insulin crystals. The first step in the final process is the synthesis of insulin crystals. Insulin is known to crystallize when exposed to zinc, and there is a great deal of literature on the crystallization of insulin. However, as we were unable to obtain an assay to test the activity of insulin crystals, our team did not attempt to grow insulin crystals for testing purposes. Instead, during the spring semester, our team worked with Dr. Snow's research lab, growing protein crystals to better understand the protein crystallization process, as this was becoming an important technical aspect of our project. Due to the high cost and complexity of insulin, our team decided to experiment with hen egg white lysosome, or HUEL, crystals, as Dr. Snow's lab has the materials and extensive experience needed to grow them. These are assumed to be analogous to insulin crystals and were used in the validation of our device. In order to grow HUEL crystals in lab, the optimal crystallization conditions needed to be determined. Our team performed a design of experiments to determine these optimal conditions. The response variable we were testing was the amount of crystals formed, and the varied parameters were the soluble lysosome concentration, sodium chloride concentration, pH, and protein concentration. The optimal crystallization conditions found from this DOE were then used to perform batch crystallization to create an optimized amount of crystals. After the crystals have been formed and collected, they are lyophilized. Lyophilization is more commonly referred to as freeze drying, and it removes water by pulling a vacuum and forcing water to sublimate out of the crystals. Lyophilized crystals are optimal for our process because their weight is easily measured, allowing for a more accurate knowledge of the concentration of the final solution. Additionally, lyophilized insulin crystals stored in a vacuum are very stable at room temperature, allowing for storage without refrigeration. This became highly important recently when Eli Lilly dropped their prices of insulin to $35 a vial. This room temperature stability allows for the production of insulin in areas and situations without reliable refrigeration, setting this product apart from others on the market.
As previously mentioned, vacuums were chosen as the ideal vessel for storing the insulin crystals as they are already FDA approved for containing sterile materials and have the benefit of drawing in the buffer solution without external work. As they are also under vacuum, the insulin crystals have no contact with oxygen, which can degrade their structure. This further improves the length of storage the insulin can undergo without refrigeration. The device shown here was used to test the efficacy of the vacuumers. It was found that they reliably held their vacuums for up to 3 uses, proving that the vacuumers are highly reliable for a single use. The vacuumer is then paired with an IV bag containing the buffer solution. As a precise amount of the buffer solution is required to ensure a specific concentration of insulin, the buffer solution will be kept in a small 10 milliliter bag. Having a precise concentration is critical, as inconsistencies could lead to doses with too much or too little insulin. While we are unable to test this solution due to time constraints, we expect this to be a good starting point if this project is continued. To combine the insulin crystals in the vacuum with the buffer solution stored in the bag, a needle is attached to the bag and is injected into the end of the vacuum. The vacuum then draws in all of the buffer solution as a pressure difference between the vacuum and bag causes suction. This will provide a simple but effective way of regulating the amount of fluid that enters the vacuum. To mix the buffer solution and insulin crystals within the vacuum, a device that does not make contact with the contents of the vacuum was developed. During the development of this device, a computer engineer assisted our team in building a user interface that made the testing of the device much more simple. In addition, a modular test bench was used to increase the speed of iteration. The UI, modular test bench, and prototype mixer can be seen in this video. We went with this design as no sterilization of the mixing device would be needed between uses. The prototype mixing device seen in this slide is roughly based off a paint mixer. As a vacuum crosses the axis of rotation, vortices form, causing both vertical and horizontal movement of the fluid. If the vacuum did not cross this axis, the contents of the vial would simply separate. As this device uses one motor, it is also highly cost effective and has far fewer points of failure than previous designs.
Inside the mixer, the insulin crystals are redissolved in the phosphate buffer. There are 2 categories of insulin, short-acting and long-acting. Short-acting insulin is dissolved in solution, while long-acting insulin consists of insulin crystals being suspended in solution. The goal of our project is to make short-acting insulin, which is why we designed a process to dissolve these crystals rather than resuspending them in solution. The video on the right shows the protein crystal we grew dissolving in a buffer. The final step in the at-home insulin synthesis process is the quality control checks. As mentioned previously, quality control is one of the most important requirements for FDA approval of a Class II medical device. Although fulfilling all requirements for FDA approval was out of the scope of this project, we wanted to ensure that these aspects were explored and incorporated into our device. In order to validate the quality of the insulin product, we performed a risk assessment. We determined that the 2 most important qualities to check were the pH of the solution and the concentration of the final solution. The pH will be checked using a pH strip and will require visual inspection by the user, and the concentration will be tested by measuring the absorbance of the solution with a spectrophotometer. In order to achieve FDA approval, more rigorous testing will be required to further control the process, such as ensuring that the user cannot inject a bad batch of insulin or that the insulin's activity is not affected. All of these components and process steps make up an innovative device that can easily produce insulin at home. The main strength of our final process is the stability of insulin crystals at room temperature. This introduces the possibility for insulin production in areas and situations where there is not reliable refrigeration. Also, this process doesn't require a clean-in-place system, eliminating the hazardous chemicals involved. Another strength of this device is its simplicity that allows it to be very user-friendly. Finally, the fluid transport system is highly precise and reliable due to the nature of the vacuum.
Once we finalized our process, we started an analysis of safety and sustainability. Because the final product of our process is a medication that will be injected into customers' bodies, a thorough review of safety hazards was critical to the success of this project. We started our safety analysis by identifying possible safety hazards within the device. We considered hazards introduced by the mixer, the vacuum, and the buffer capsule. The vacuum had the most possible safety hazards of the 3-unit operations. Because the insulin crystals are stored in the vacuum, any malfunctions could critically damage the quality of the resuspended insulin by compromising the quality of the insulin crystals. The hazards introduced by the mixer are more mechanical in nature. The mixer's mechanical components could malfunction, resulting in damage to the device. The buffer capsule has the least amount of possible hazards, with only the risk of preemptive puncturing or an incorrect amount of buffer solution. Although there is always some risk that these hazards will occur, we are implementing mitigation strategies to reduce their likelihood. We will conduct extensive quality checks on the vacutainer and buffer capsules to ensure that they can be safely distributed. We will also provide training manuals for customers with instructions on how to care for the mixer, which should prevent its mechanical damage. The device will also have a built-in control system to ensure that insulin is being properly produced. After we considered the safety of our process, we moved on to an analysis of sustainability, examining the 7 indices of sustainability in more detail. This radar chart summarizes the ratings for each of the indices of sustainability. Environmental performance, sustainability, innovation, and social responsibility are the indices with the highest average ratings. These have all been areas of a high priority for the Open Insulin project. The at-home insulin generation device was developed to help the millions of diabetics struggling from the inaccessibility of insulin. Since the project has always been focused on social injustices, maintaining social responsibility is crucial for the credibility of the project. Similarly, the purpose of the project was to create an innovative and novel method for the production of insulin at home. Therefore, the high rating for sustainability innovation accurately reflects the goals of the Open Insulin project. Environmental performance is also important to the values of the Open Insulin project. Although the at-home insulin generation device could serve to help individuals with diabetes, it could do more harm than good if environmental protection is sacrificed and entire communities are impacted. On the other hand, project stewardship and strategic commitment have the lowest average ratings. This is due to the current stage of the project. Since the project is still in the research and development phase, the metrics for these indices are not applicable to the Open Insulin project. It should be noted that the Safety Performance Index has an average rating of 5, making it one of the 3 lowest rated indices. Safety is another crucial priority for this project. However, without thorough safety testing, it is difficult to accurately assess the safety of the at-home insulin generation device. Future work for this project will improve the safety performance rating by conducting extensive safety testing.
Here we can see some of the components that go into our techno-economic analysis, including our inputs and the outputs of interest for our product. The techno-economics is really done to determine a final price of our insulin, as we want a venture that is profitable, but we do not want to put too much strain on the backs of our customers. So we are doing this by balancing the price of our insulin with our rates of return, keeping them around 20%. Here we can see the anticipated initial cost to our venture. This includes everything needed to grow crystals as well as the facility to facilitate this need. Next, we can look at our anticipated annual sales. These projected orders come from looking at the total number of people in America who suffer from diabetes and assuming we can get 5% of that market pool, or around 2 million people. We assume that each user will need their own synthesis device and order about 12 vials a year, coming to a net annual sales of $1.3 billion a year. Next, we looked at the labor required to facilitate this operation. We assume with our projected annual sales, we will need about 41 people to operate all this. So that's broken down into 3 groups: the assembly line operators responsible for the assembly of the device, as well as packaging of the insulin; quality control people growing the insulin and controlling the growth; and manufacturing supervisors focused on big picture items. We've calculated their annual yearly salary and included some multipliers to cover for things like 401k, health insurance, and other services that we as hiring managers would need to provide to our workers. Next, we looked at our feedstock, or the raw materials we need to grow our products. These come directly from our anticipated sales numbers. And we also looked at utilities. This is everything to keep the lights on and the equipment running. The general operation overhead comes from repairs that we would need to make to our total depreciable value. So this is equipment repairs, factory upkeep, as well as other services that we would need to make to get our product to our consumers. Finally, all this culminates to our cumulative cash flow estimation for the foreseeable 5 years. As you can see, we have a net present value of $734 million, a venture profit of $343 million, a return on investment of 26%, an internal return on investment of 110%, and a payback period just above 3 years. Our final price of insulin was confirmed to be $50. This is considerably cheaper than the average price a user pays for insulin in America. And the only other real competition is Eli Lilly, just releasing their $30 vial of insulin. However, our stability and shelf life for our product should still make us competitive even against them.
Over the past year, the Open Insulin team collaborated to identify, design, and develop a prototype for people with diabetes and limited access to insulin or refrigeration in the United States and third world countries. With the big three companies holding a monopoly on the insulin market and tightly regulating patents, it was essential that the team focused on a simple yet effective synthesis method to compete with the current market. After identifying insulin crystals as a precursor, it was noted that the proposed process would be cost-effective, user-friendly, and would remove the need for refrigeration prior to use as a result of the crystal's enhanced stability. The development of the mechanical device was subjected to several iterations. The primary design consisted of fluid transport and CIP, but was simplified in the second semester to contain only a single unit operation. By using a vacutainer, the solution can be prepared with minimal contamination and loss of product. This also optimized the safety and sustainability associated with the device. As a medical product, it's imperative that the device holds safety paramount, reflected by the analysis of each component's risks and remedied by quality control and control systems implementation. The sustainability of the device was also evaluated, and it was concluded that environmental performance, sustainability innovation, and social justice represented the strongest of the 7 indices. Finally, the techno-economics were considered, and a final price of $50 was identified, with a return of investment of about 20% and an internal rate of return of 140%. Although the economics may be improved, profitability was not the primary objective of this project. We recommend that this project continue next year and would like to highlight suggestions for future directions. The work completed this year was primarily based on literature, so it's recommended that more thorough testing is conducted on the proof of concept to verify the stability of insulin crystals and test their functionality after dissolution. Additionally, an in-depth analysis of the upstream production process for the crystals will need to be incorporated into the project. Future work will also include a detailed plan for FDA approval and extensive safety testing of the device and insulin. Our team would like to thank our advisors, Dr. Christy Peebles, Professor Bert Vermeulen, Professor Minnie Pifferario, and Mike Martinez, without whom our project would not have been successful. We've gained hands-on professional experience throughout this project and are excited to see how it evolves in the future. Thank you to all of those who helped us succeed, and thank you for taking the time to listen to our presentation.